We know we're talking about vibrating strings and their wave equation. So we want to model a vibrating string by obtaining the partial derivative equation of partial derivative equation modeling of small transverse vibrations of elastic string. So we place the string along the x-axis, then stretch it to a length L, and fasten it at the end x equals 0 and x equals L. We then distort the string at some time t equals 0 and release it, letting it vibrate. Therefore, the problem is to determine the vibrations of the string. Which means to find the deflection u depending on x and t at any point x and at any time t major to 0. So the model consists of a PDE and some or certain additional conditions. So in order to obtain the PDE, we consider the forces acting on a small portion of the string. Let's consider that the string has some shape like this, where this is the x-axis, this is the function u, this is 0, and let's suppose that the string has at a given time a fluctuation as this one. So let's suppose we have a point x and a point x plus delta x, and at this value we have a point in the fluctuation at x equals to p and at x plus delta x equals to q. So we know that this shape have a tangential force which is actually the tension that the string is submitted to. So this angle will be equal to alpha, and this angle here will be equal to beta. Let me write that again. Okay. So we know that the tension is tangential to the curve uh, to the curve of the string at each point. Then we know that T1 cosine of alpha will be equal to T1 cosine of beta is equal to the tension, and this will be a constant because it's the same throughout the whole string. So the component of this tension in a vertical, the component in the vertical direction of the vibration of the string can be defined as follows: minus T1 sine of alpha is equal to rho delta x d squared u over dt squared. So this is dependent on the second Newton's law. So what we are doing here is just making an addition of the forces by which the string is submitted to, and we're making this equal to the mass. It's defined by this, the density and the delta x times the acceleration of the string. So we can divide by T2 cosine of beta equals 1 cosine of alpha equals to theta, and we have equals to t. So we have T2 sine of beta over T2 cosine of beta minus T1 sine of alpha over T1 cosine of alpha is equal to rho delta x over t d squared u over dt squared. And this will give us the same, this next value, tangent of beta minus tangent of alpha would be equal to rho delta x over t d squared u over dt squared. However, we know that the tangent at the angle alpha is equal to the partial derivative of u with respect of x, because that's the definition of the partial derivative at the given point x. That can be seen in the graph, where the tangent at the angle alpha is equal to the derivative of u with respect of x at the given point x. So now we also know that the tangent of the angle beta is equal to the partial derivative of u with respect of x at the point x plus delta x. So we can then divide by delta x, and we'll have 1 over delta x times the derivative of u with respect of x at x minus delta u over the derivative of x at the point, this is x plus delta x at the point x, because it was tangent of beta, and we just write it here, and this is equal to rho over t times d squared u over dt squared. So if we let delta x to tend to 0, we then get that d squared u over dt squared is equal to c squared of d squared u over dx squared, where c squared is equal to t over rho. And there we have the partial derivative equation of the vibrating string.